Hello everybody! In this clip we discuss resolutions of singularities and mainly deal with the surface case. First, a resolution of singularities of a variety X is a proper birational morphism from a variety X' onto X such that X' is smooth. In the world of toric varieties, the proper birational toric morphisms correspond to refinements of lattice fans. That means that we have a fan sigma prime and a fan sigma living in the same lattice, having the same supports, and for every cone small sigma prime we find a cone sigma containing our sigma prime. Let us look at an example. Consider the cone generated by the vectors 1, 0 and 1, 2. We know already that the corresponding affine toric surface has a singularity, namely the limit point small x sigma. Now if we insert a new ray into this cone sigma, the ray is ruled at the point 1, 1. Then we obtain a fan, and all cones of this fan are regular by construction. That means that the corresponding surface is smooth. Moreover, this is a refinement of fans. So we have a proper birational morphism from x capital sigma to x small sigma. And this is a resolution of singularities. Let us prepare the general case. Look at the cone generated by the vectors 1, 0 and AB, where A and B are non-negative integers, A strictly smaller than B, and we want AB to be co-prime so that V infinity is a primitive lattice vector. The observation is that the vector V1 equal 1, 1 is the unique lattice vector in sigma, having determinant 1 with V0, and being indecomposable in the cone monoid. Indeed, all vectors of determinant 1 with V0 lie on the axis shifted to height 1. Some of them are inside sigma, and our V1 is the one closest to the boundary of the cone. Moreover, if B is greater than 1, then determinant of V0 V infinity equal B is strictly bigger than B minus A, which is the determinant of V1 and V infinity. Now look more generally at any two-dimensional lattice cone sigma naught with primitive generators V0 and V infinity. From our previous observation we infer that there is a unique indecomposable element in the cone monoid of sigma naught, having determinant 1 with V0. We insert a new ray through this element V1 and thus subdivide our cone sigma into two cones, tor1 and sigma. Then, if V1 differs from V infinity, the determinant of V0 and V infinity is strictly bigger than the determinant of V1 and V infinity. And moreover, for the Hilbert basis of all our cones, we have that the Hilbert basis of sigma naught is the union of the Hilbert basis of tor1 and of sigma 1. We are ready for the general statement on resolution of toric surface singularities. Consider any two-dimensional lattice cone with primitive generators V0 and V infinity, we want to construct a regular subdivision of the cone sigma. The idea is to enter with sigma naught equals sigma this procedure here. We take this element V1 in case that V1 equals V infinity, then our initial cone sigma is already smooth and there's nothing to do anymore. If not, then we insert this ray through V1 and subdivide into two cones. Tor1 is regular, and sigma 1, the other cone, has a determinant V1 with V infinity strictly smaller than determinant V0, V infinity. Now, if we iterate this procedure, in each step the determinant decreases. That means that after a finite number of iterations we end up with Vn equal V infinity, which gives us a lattice span capital sigma in C2, such that the set V0, V1 up to Vn equal V infinity are the primitive generators of sigma, and moreover they form the Hilbert basis of the cone sigma. By constructions, all the cones tor I for I from 1 to n are regular. That means that the corresponding toric morphism from x capital sigma to x sigma is a resolution of singularities. We want to discuss a bit the geometry of our resolution of toric surface singularities. This involves intersection numbers. Recall that given any smooth surface x, a smooth irreducible curve on x and a Cartier divisor d on x, such that the curve is not contained in the support of d. Then we can restrict the divisor d to the curve. Remember that d is locally the divisor of rational functions. We just restrict these rational functions to the curve, look at their divisors on the curve and put these divisors on the curve together. This gives our restriction. The intersection number d dot c is defined as the degree of this restriction, and this in turn is just the sum of the coefficients of the restricted divisors. If the curve C is complete and we have another Cartier divisor d prime which differs only by a principal divisor from d, and C is not contained in the support of d prime, then the intersection numbers d dot c and d prime dot c coincide. This allows us to define self-intersection numbers. If d equals c, then the self-intersection number c square is defined and computed as d prime dot c. Here is how we compute intersection numbers on toric surfaces. Consider a fan sigma in a two-dimensional lattice. Assume that all cones of sigma are regular. That means that the corresponding toric surface is smooth. Denote by V1 up to V are the primitive generators of sigma, and write di for the toric prime divisor corresponding to the ith primitive generator. Then di is a Cartier divisor on the one side and also a smooth irreducible curve on the other side. Now for two distinct I and j, the intersection number di dot dj is 1 if the cone generated by vi and vj belongs to sigma, and 0 otherwise. Moreover, if you have two adjacent cones, then the self-intersection of the divisor dj corresponding to the ray in the middle is minus m, where minus m is the unique integer such that vi plus vk equals m times vj. Now look again at our resolution of a toric surface singularity given by subdividing along the Hilbert basis. Then we can say the following about the geometry of this resolution. First, over capital X sigma minus the limit point small x sigma, that means the smooth locus, the map phi is an isomorphism. Moreover, the fiber over the singular point is the union of the toric prime divisors corresponding to the rays rho 1 up to rho n minus 1, and each of these divisors is a projective line. About the intersection numbers, for I less than j, di dot dj equals 1 if j equal I plus 1 and 0 else. The self-intersection numbers of all the divisors corresponding to the rays inside sigma are all less or equal to minus 2. Finally, this resolution is minimal in the sense that whenever we have another resolution of singularities, this resolution factors through our resolution phi. Let us see an example, the example from the beginning again. So we had the cone sigma generated by 1, 0 and 1, 2. The resolution was obtained by inserting the rays through 1, 1. Now 1, 0 plus 1, 2 equals 2, 2. That means that the self-intersection of the divisor d1 equals minus 2. We end with a remark about the general case, that means higher dimensions. Every lattice fan has a regular refinement such that all regular cones in our lattice fan sigma occur as well as cones in the refining fan sigma prime. This is also obtained by inserting rays in a certain way, but is not anymore as canonical as it is in the surface case. See you in the next clip.